We'll continue where we left off. So we were looking at the electric force between charges. We found that it's described by Coulomb's law, which is just this right here. It says that the size of the force depends on how big the two charges are and how far apart they are. And that's about it. The only thing extra is that number k, and it's just needed to make sure you get the correct force out when you multiply all those things together. If we're dealing with more than one charge exerting a force on a charge we're interested in, we have to do vector addition. And it's the same kind of vector addition as you learned in Physics 1. We're just now doing it with electrical forces instead of friction or tension or gravity or whatever else. And so we started looking at an example of that last time. We had a proton in the middle, and we wanted to see about the forces on it from an electron and another proton. We found that the electron attracts it, meaning pulls it to the left. That's the force 2 exerts on 1. And now we're going to put down the force that 3 exerts on 1. So what direction would that be, that force?
Wouldn't it also be to the left?
Yep, because it's going to repel that proton, so it will also push it off to the left. And in fact, since it's the same distance away as the electron and it has the same charge as the electron, just positive, that force is equal in size to F2 on 1. And that is all the forces acting on charge 1. So to find the net force is vector addition, but these are both along the same line, so it's pretty easy. You just add those two vectors together to get the net force on charge 1. So if we want to put numbers to that, it's pretty straightforward. It's that the net force is the vector sum of these two forces. But if we want to actually use numbers, it's easier to do that as a component-wise addition, meaning instead of this vector addition thing, which kind of just means that graphical thing we just did, let's turn this into two separate equations, one in the x and one in the y direction. So the y is easy. What's going on in the y direction?
Nothing.
Nothing. So the net force in the y direction is 0. For the x direction, we just have to remember that for components, we're saying which way is that vector facing. Is it to the left or to the right in the x direction? Or for the y, is it up or down? So both of these were to the left. And to account for a leftward facing vector, we use a negative. So here, negative means to the left. And that is for both F2 on 1 and F3 on 1. I could have just written that as minus F2 on 1 and then minus F3 on 1. I didn't really need the plus. This is just to emphasize that I am really adding these vectors. They just happen to both point to the left. And then the last thing would be, if I really wanted to get actual values out of this, I have to remember, well, what is that force? What is the size of it? This is like when you were in Physics 1 and you found that something depends on the weight of an object. But then you remember this next step, which is that weight is mass times g, and then you can actually calculate the weight. This is similar to that, but now you remember that the electric force is given by Coulomb's law. So the force 2 exerts on 1. You need those two charges, 1 and 2, and then the square of the distance between them. On my picture, that distance is this right here, R1, 2. And then for F3 on 1, it looks almost exactly the same. It's just now it's charge 1 and charge 3. And then the square of the distance between them, which is this distance right here. I'm sorry, it should not be an equal sign. It should be just a add those two together. So this one, this force is F2 on 1, and this is F3 on 1. And the only number we don't have to actually put into this is R12 and R13. We have the charge values because it's an electron and a proton. We know those charges. So we could, aside from those distances, get an actual number out of this if we wanted to. But I'll stop it right there. So any questions on that one? What you'll probably notice is the math looks a lot worse than what we actually had to do to find all those numbers. And so I think the takeaway is that for these kinds of problems, it's not so much that the problem's hard, it's that there's so many steps. And if you miss one of the steps, it's pretty easy to get lost on what you need to do next. So I'm going to be a little bit more explicit about what steps I'm taking to do this next one because it's a harder problem. So my first step will be, I want to find the net force on charge Q1. I want to draw in those vectors, but only for the forces that are acting on charge 1. That's that thing again of, yes, things are attracting, yes, things are repelling, but I really only care about one side of that attraction or repulsion right now, whatever of it is happening to charge 1. So let's go ahead and do that. We've got a negative charge up here. I will point out it's in microcoulombs. We'll see how to deal with that in just a minute, but that is going to be something we have to deal with. And then I've got another negative charge over here. What will those do to that positive Q1 charge?
Attract it?
Yes. And so Q2 will pull Q1 towards it, and that's what I'm interested in. What happens to Q1 as a result of this interaction? I don't care about this other side of it that Q2 is also attracted, because that's not what I'm being asked about right now. So I won't draw it, because that'll just confuse me. So this is F2 on 1. And what about charge 3?
It will also attract?
Yes. So F3 on 1. And so essentially what we've just done is drawn a free body diagram for charge 1. If you like, you can actually separate it out and say, all right, here's charge 1, and I'll transfer those forces that are acting on it. I'll be lazy about it and I'll just copy and paste them. But that's essentially what we're doing here is, just like in physics 1, finding all the forces on this charge and turning it into a free body diagram. What is the next step if you are finding the net force on something after you've made that free body diagram?
Get your axis.
Yeah. And here there's no like best choice necessarily because I can't get everything to line up on an axis. So I'll just go with the standard of left to right is the x-axis and up and down is the y. At a certain point, I will kind of be lazy and not even separate out the charge. Like, I probably would typically just stick with the original picture and analyze things on there. But this is just to point out, I'm still just doing free body diagrams. It's still physics 1 type stuff. And so our next step is, now that I've picked my axes, find my components for those forces. And I like to make a table for that. If you did it a different way in physics 1, do whatever's comfortable. It's the same process you learned then. I'm not doing anything new just because it's about electricity now. So I've got 2 forces acting, and I want to figure out how to add them to get the net force on charge 1, which I think in physics 1 I used sigma F to say net force. I don't know why I've pivoted to saying F1 net, but it's the same thing. So finding the net force on charge 1 is our goal. So tell me about, let's start with F3 on 1. Tell me about its x and y components.
Y is 0.
Yep, it is pointing completely to the right. It has no up or down component. And again, I'm looking at this vector right here. Okay, is it pointing to the left or to the right? So positive, negative or positive, I should say.
Positive.
Positive. It is pointing to the right, and all of it is pointing to the right. So I don't need a sine or cosine. All right, that's it for F3 on 1. Now for F2 on 1. Is it pointing left or right and up or down?
Up.
It is pointing up, so where would that go in my table? What kind of label would I do for that?
The y component would be positive.
Yep. Okay, and then what about the x component?
It would also be positive.
Yep, because it is pointing to the right. So just a reminder from physics 1, positive in the y means up, positive in the x means it's to the right. And now is the hardest part, which is whether I use sine or cosine. So I think of it as it's going to be some fraction of f2 on 1 of the length of this vector. Some portion of it is in the x direction and some portion is in the y direction. I just have to figure out what portion. And to do that, I need to sketch in those components. So I'll do that down here. f2 on 1 points to the right, and it points up. And remember to sketch in components, you're just saying I'm only allowed to draw arrows that point left or right and up or down to get from one end of the vector to the other. So this is f2 on 1x and f2 on 1y. And then this angle from the picture up above is 73 degrees. So for f2 on 1x, should I use... Oh my goodness, no, that's a stupid mistake. This is the y component because it points in the y direction. This is an x component because it points in the x direction. Okay, for f2 on 1y, should I use sine or cosine?
Sine.
It's going to be sine because I have to go opposite the 73 degree angle to get to it, and that so part of SOHCAHTOA, sine is opposite over hypotenuse, tells me that sine correlates with opposite, and then cosine will be this one because it's adjacent to that angle. It touches it. So yes, for f2 on 1y, I will use sine 73. Okay, and then I will use cosine for the x. Now what?
We add them up.
So I will add down these columns to get the overall x and y components. So this will be f2 on 1 cosine 73 plus f3 on 1. And then this one is just f2 on 1 times the sine of 73. Okay, and on my picture over here, what I'm finding is the overall x and y components that I get by adding this to this. That'll give the overall x component, and then the overall y component is just this because the red vector had no y component. So my overall might look something like about this far out, just adding those red and green ones together. And then about this far up. So my net force is going to be something like this, but I still need to find the size of those two components, meaning I'll call F net x and F net y. So how can I put numbers to these? Well, I have to remember what F2 on 1 is, where it comes from. It's an electrical force between 2 point charges. So my rule for that is Coulomb's law. Again, this is the thing that's like using mg to find weight, or using coefficient of friction times normal force to find friction. It's that extra step you have to do that depends on the type of force you're dealing with. So my step 3 is, we'll say, use Coulomb's law. And what I mean by that is I can find a number for F2 on 1 and F3 on 1. By remembering that it's equal to that number k times the size of the two charges involved over the square of the distance between them. K is that 8.99 number. It just tells us, given two charges in a certain distance, how large is the force between them. This number is needed to make sure you get the correct value. All right, for Q1, it's 4 microcoulombs. Anyone remember what micro means?
Do you mean like the exponent value?
Yes.
It's 10 to the negative 6.
Yes. So that one, it'll sneak up on you. It's tempting to just write 4 and call it a day, but it's 4 times 10 to the negative 6 coulombs for Q1. And then for Q2, it's negative 6. The negative's going to turn out not to matter, though, because I'm using that absolute value, because I just care about the size of the charge. And then the square of the distance between the two was, the distance is 0.15 meters. We square that, and so I get 9.6 newtons for that first one. I want you to take a minute and try and do this for F3 on 1. So just see if you can get a value for it, and in a couple of minutes I'll let you know what value I get. Does anyone have a value for this?
I got 17.9.
That sounds good to me. I'm gonna just round it up to an even 18, but that is also what I get. So if you don't want to rewrite all this stuff, because most of it is similar to what we just wrote, you don't have to. But it's K. Q1 is the same as before, 4 microcoulombs, and then Q3 is -5, but again, the negative is not critical because we're taking an absolute value. If you want, you can just throw it out completely. Sometimes that leads to less confusion of whether you should keep a negative or not if you just throw them all out at the beginning. But then the distance between charge 1 and charge 3 is 0.1 meters. We square that, and I do get something like 18 newtons. Okay, so now we have values for that. Now what can we do?
Do we add
Plug
them
them
together?
in.
Yeah, so I would call this calculating your components. I know that looks similar to step 2, which says find your components, but you can see this is actually putting the numbers in. And that is a part or a step that is often kind of mashed up with step 2, when really we kind of need a little bit more information to be able to do it. So the net force in the x direction is F2 on 1 cosine 73 plus F3 on 1. And we now know that's 9.6 cosine 73 plus 18. Comes out to something like 21 newtons. And then in the y direction, we had F2 on 1 sine of 73. So 9.6 sine of 73, or about 9.2 newtons. And so now I've actually found the value for these two components. So the horizontal is about 21 newtons. The vertical is about 9.2. How do I finish this out? So what I ultimately want to find is the size of the overall force on charge 1 and the direction it acts. By direction, I might say something like, well, what is this angle right here? How would I find those two things, the magnitude of the force and its direction?
Would you do the square root of the net force in the x direction squared plus the y direction squared?
Yep, we're back to Pythagorean theorem and inverse trig stuff. So find F net and theta with trig is our last step. So the net force comes from Pythagorean theorem. The x was 21, the y is 9.2. Take a square root of all that. I get something like 23 newtons. And then the angle, inverse tangent of y over x. So again, this is a physics 1 thing, but where that comes from is if I look at my diagram, tangent of theta is opposite over adjacent. That's just how we find tangent. And so that would be the opposite side is this right here, or F net y. The adjacent is that right there, or F net x. And so theta itself is the inverse tangent of that ratio. But one thing I like to do just to avoid confusion is these components can have negatives because the vector could point to the left or it could point down. That's going to show up in your calculator as a negative, but that's more confusing to interpret for an angle. So I like to pop absolute values on here, saying ignore those negatives when I'm calculating this, because I can tell from my picture which angle I'm talking about, whether I mean from the x-axis or the y-axis or however I'm measuring the angle. And throwing those absolute values in there helps to avoid some of that confusion. Absolute value, absolute value. The y component was again 9.2. The x was 21, so here I didn't really need the absolute values because they were both positive anyway, but that's just sort of a precaution. I get 24 degrees. And if you want, you could say from the positive x axis. So that is a lot, I know. And in this next section, we're going to do something very similar to this, and it's just about as bad. But this is what I mean by it's really, the steps are not so hard in and of themselves. It's just that there's so many. So for things like exams, since you have a cheat sheet, something like this of just saying what you should do with each step is going to be a good thing to write down, because again, you're not messing up because you don't know what to do. You're messing up because you don't know every little detail of every little piece of what needs to be done, because there's just so many. And let me throw a curveball here. What if all of a sudden I said, all right, instead of Q1 being 4 microcoulombs, it's now 8. Do the problem again. How would you feel about that? I guess that is kind of rhetorical. Probably not great, because it's so many steps all just to get this one result for just these 3 charges. So what if I said I have a shortcut? Now that you've done this once, you can do it very easily if I replace Q1 with anything else. All you have to do is notice, let me kind of hunt back through these calculations. So I had to find Fnet X and Fnet Y, for instance. But if I look at those, they relied on F2 on 1 and F3 on 1. If I look at F2 on 1 and F3 on 1, they relied on Q1, Q2, R1, 2 squared, all that stuff. What I'm noticing is that Q1 shows up in every term. Because it shows up in F2 on 1, that means it shows up here. And since it's in F3 on 1, it shows up here. But then that means it's going to show up in the X and Y components. So you don't need all these arrows on your paper because it's a mess. I'm just trying to illustrate this. But that also means they're going to show up here. And so if I follow that algebra through, what I'll find is Fnet can always be written as Q1 times something else. And that something else only depends on the other 2 charges. So if those changed and I wanted to find the force on Q1, that would be a little trickier. I would have to go back and redo some stuff. But that's because, thinking a little bit more abstractly, the surroundings of Q1 have changed if I do that. So Q1 is now sitting in sort of a different space if I swap out Q2 or Q3. If I swap out Q1, I'm just bringing something else into that same space. I'm setting it into that pond that exists as a result of Q2 and Q3, and Q1's just sort of experiencing it, riding the waves of it. So that's the philosophical kind of view of what we're going to talk about next, the electric field. In that context, forces are this interaction between some object, an interaction between Q1 and this other thing that's in parentheses, which we're going to call the electric field, created by Q2 and Q3. That's this thing over on the right. And so by doing that, one, like I said, it makes the math a little easier because you don't have to reinvent the wheel just because you swapped out for a different charge. But for 2, it kind of gets at the idea that every charged object carries this thing with it, this electric field, and forces arise because of an interaction between that field and other objects. So that's where we're headed. How is it that things can exert forces on each other from a large distance away? Because they're not really the thing that's important. It's the fields they create around them, these sort of invisible things that other objects interact with. And so it sounds a little bit, I don't know, mystical, and that's not really what I'm trying to go for, and this definition's not going to help that feel, but it will maybe give you kind of a gist of what to think about. So I'm going to call the electric field an aura, which I don't like that word, but kind of gets the idea across. Surrounding every charged object that extends throughout space, meaning it exists everywhere around the object. It does get weaker as you move further away from the object, but it is still present. And the reason this feels sort of mystical and abstract is because we can't see these things. What we can do is hold a charge up in a space we suspect one of these electric fields to exist in, and we see what happens to that charge. So we measure the effect of this field on a charge, and that's how we know it's a real thing. That's where it becomes not so mystical, is that you see something happen to a charge if you put it into a place where an electric field is present. So we call that measuring device, that charge we use, a test charge. A tiny positive charge. Positive is important because we always want to use this same type for consistency. You'll see what I mean in a little bit. Used to measure the strength of a charged object's electric field. I'm going to draw an analogy with gravity because this may feel a little bit more familiar or like something you could picture, but the same ideas will apply to the electric field. So say you go to some distant planet. You know nothing about it. You get out of the spaceship and you want to start learning things about the planet. How could you test how strong the gravity is on this planet?
Like put something in orbit around it, maybe?
You could. That'll tell you something about it. There's something even easier you could do. Just a human being stepping off a ship.
Jump?
You could jump, so you could act as this test object. There's something that requires even less effort on your part.
Drop something?
Drop something. Pick up a rock and drop it. And if it looks like it falls a lot faster than on Earth, you can conclude that gravity is stronger on this planet. If it falls slower than on Earth, gravity is weaker. And that's telling you something about the planet, not the rock you dropped. So you could have dropped any rock and observed something like this. The rock is just a testing tool to conclude something about the planet. Okay, so you go around, pick up a rock, and you may notice that it falls towards, well, let me make that more towards the center of the planet. So it falls downward wherever you're standing at some rate. And that tells you something about the force of gravity here. If you go elsewhere on the planet, you do this again, you might actually notice that the rock falls faster if, for instance, there's a concentration of mass beneath you. There's some mountain range kind of something going on. But maybe over here, it falls a good bit faster. So you conclude gravity is a bit stronger over there. And then you climb up high. You climb up on this ladder. You drop your rock, and it falls maybe a little bit slower because you're further away from the surface. Now, would you actually be able to tell a difference just using your eyes for those things? Maybe not, but that's the idea we're trying to get across here. And in all cases, it's not the rock that's the important thing. It's just a means to an end. So we call it a test mass. We'll call it M0. And we use it to gauge something about the planet. We call that thing we're gauging about the planet its gravitational field. And we'll define it to be the gravitational force on that test mass, on that little rock, divided by the mass of the rock. The mass is the universal thing, that it'll be the same no matter what planet we're on. Reason we divide by it is, say I used a rock that had twice the mass of the one I'm currently using. What would happen to the force of gravity on it? So make this feel more like planet Earth. If I have a rock of twice the mass on planet Earth, what happens to its weight? How hard it's pulled by the Earth?
It gets pulled harder.
Yeah, it's twice the pull. But is that a statement about the Earth or about the rock?
A little of both.
In a sense, like the Earth is the thing pulling in both cases, but did the rock feel a greater force because something about the Earth changed, or because I swapped rocks?
A different rock. So,
Yeah, it's a
because you swap.
right. So That is an artifact of what tool I used to test. It's not something about the Earth itself. So the reason I'm dividing by this mass is to kind of get rid of that effect of which rock did I use. Because if I use a rock with twice the mass, yes, the force of gravity doubles, but so does this mass, and so the ratio of them does not change. That's getting at something that's a property of the Earth itself. And in particular, from Physics 1, we remembered that the force of gravity is mass times g. And now I see why this is independent of what rock I use. Because this comes out to that number g, which on Earth is 9.8. On a different planet, could be something totally different. On Jupiter, it's like 19 point something, I think. On the Moon, it's 1.6. But you can see this thing is purely a property of the planet, not the rock. I used the rock to measure it. That's what I was doing over here, finding the force on the rock and then dividing by its mass. But it got me to something that is strictly a property of the planet itself. And so the other thing is that g, that number we just call gravitational acceleration, is actually what we call the gravitational field of the planet. So our conclusion is g is something that's created by the planet itself, and in particular the planet's mass, which I'll use, say, big M for. It's something that's only going to change if I go to a different planet or I go to a different part of this planet where there's a lot more mass concentrated. The rock mass is just used to test g. And then if I bring in a different thing, could be a rock, could be me, could be any other object, I now know something about how it will interact with this planet. I just take its mass and multiply by g instead. That'll give me the force on that new object. So I've found something, I've cataloged something about the planet itself by doing this intrinsic thing it creates, this g value. We're going to take the same idea and transfer it over to the electric field. In this case, it's not some mystery planet I want to characterize, it's some mystery charge. We'll call it big Q. I say it's creating this electric field around it. I can't see that field, but I do want to know about it. So the only option I have is take a little test charge. This is my rock I pick up. And I just hold it at different places around that big charge and see what happens to it. Over here, it might be repelled. So this is the force on that little charge. If I hold it closer, it'll probably be repelled even more because the distance got smaller, so it's a stronger force. And it's repulsive because, remember, my test charge I'm going to take to be positive. And I just keep doing that at different points to gauge things about this charge in the middle. I may find a different direction and a different size for the force over here, and then over here, and then over here. And I just keep doing this at different places, and I'm sort of cataloging something about that big charge in the middle. And I'm going to take that information and use it to define what I call the electric field of the big charge. So yes, I'm using the little test charge, the Q0, to measure this thing, but I'm getting at something that's strictly a property of the big charge in the middle. I do that by saying measure the force on the little charge, divide by the size of that charge. I'm going to do absolute value. It's not really important because it's a positive charge, but just to say we've already dealt with the direction information by measuring that force. And we're going to call this thing the electric field. Similar takeaway. E is something that is only created by that big charge in the middle. The test charge is just used to test that field. It's the rock you hold out and drop and see what happens. And it eventually tells you something about the big charge itself and what it's creating in the space around it. So that's the electric field, and that throwing out thing is again the idea that it should not depend on what charge I used or what rock I dropped. So I'm going to divide by it to, in a sense, get rid of that effect. It should not depend on if I doubled the test rock mass or I doubled the test charge size, so those things get divided out. And that is our electric field. So you measure the force on a little test charge, you divide by the size of the test charge, and that will tell you something about the thing you're holding the test charge up to. Force on a test charge, size of that test charge, will tell you about the field of the big charge, which we called Q. And the diagram over on the right is just sort of showing the procedure I just talked about. You measure the force. If you divide by it, you get something that is strictly a property of the thing you're holding that little charge up to. In this case, this is like a PVC pipe. All right, well, you could say at this point, maybe it makes sense, but I don't see the point still. I don't see what this is useful for. And the use is, coming back to what we just did up here, that once I define the electric field and once I measure it at every point around an object, it's much easier to predict what that object will do to other things you hold nearby. All I do is take the charge of that other thing I want to know the force of and multiply it by that electric field. That's much simpler than doing all of this trig and calculation and stuff every single time I want to measure the force between two things. So that's the idea. If I have some new object, I'll call it Q new here. So I'll put a little subscript new on that charge. And I want to find the force on it. It's much easier now that I've measured the electric field of the thing I'm holding it near. All I do is take the size of that new charge I want to find the force on and multiply by the electric field. So we'll say this is the force on some new charge. This is the size of that new charge. And this is the electric field, which is created by other charges, created by some other charged object. So I kind of like to think of this like you are an inspector. So you come up to some unknown charged object, let's say a PVC pipe like we were using at the beginning of the class. You know it's charged, but that's about all you know about it. Well, to find out more, you just pull out your little test charge out of your pocket. Since you're the inspector, that's your tool of choice that you bring to these jobs you have to do. You measure the force on that little test charge over and over at different points around the PVC pipe. And then you divide by the size of the test charge you brought. Because if you brought a different test charge that day, you don't want the answers you're getting to depend on which one you brought. So you divide that out. And what you end up with is a number that describes the PVC pipe itself. And it's not only a number, it's a number with a direction, a vector, at every point in space around that object. And what you can do now for someone else coming by is you say, all right, here's my readings of the electric field everywhere around the PVC pipe. If you want to know the force on anything you've got with you, whatever charges you've got in your pocket, just pull that charge out, multiply by the field values I measured, and you're done. You don't even need to measure anything. It's much easier for you. So the hard part is being the inspector. After that, it's much easier to do this job of finding the force on things. And that's kind of what we'll do for part of the rest of this chapter is be the inspector, find the electric field for different types of charged objects so that it becomes easier to find the forces on other charges we place near them. Okay, and that puts us at 11:15, so we'll stop there. Are there any questions on any of that?
What is the SI units for?
Man, I have a bad habit of this. Thank you. So the units are the units of force, so newtons, per the units of charge, which are coulombs. So newtons per coulomb. And you can think of that as the force per amount of charge that you brought. Okay, any other questions? Okay, if not, hopefully I get to see y'all in person on Wednesday. Looking outside, that doesn't seem super promising, but we'll just see what happens with that. Have a good day.